This is our first lesson in integrals, and today we're going to actually learn how to move past approximations, which is what we were doing in the previous lessons. We were doing Riemann sums, making all the rectangles. We need to move past that, which is an approximation. We need to come up with a way more sophisticated and accurate way to get the area below a curve. And so what we're talking about is any curve that we have going from point A to point B, finding all of that area under the curve. So our first example is using just a basic equation 1/2 x plus 2 and using integral notation. So now we're going to move to how do we actually write these? What do they look like? Last week we were talking about summing up or adding up all of the rectangles from 1 to n, however many we were going to make. And this was our area. We were doing base times height. And what that's going to turn into from now on is this symbol, which is the symbol for integral. It's kind of like a stretched out S. And the low number is going to be on the bottom, A. The high number is going to be at the top. So you're saying from where to where you're going to do the integral. And then you'll have your function in front. And you throw a dx on there because we're doing all of our integrals with respect to x. Our first example is using that 1/2 x plus 2. And so to write that in integral notation, we are literally just going to write our s, our stretched out s there. 0 to 10, so 0 goes on the bottom, 10's on top. The function is 1/2 x plus 2, and then you just throw a dx on there. So that is how you write in integral notation. Again, just putting the 0 and 10, and then your function goes in front. The dx needs to be there for notation. It's kind of like learning when you write f of x. You need that there so everybody knows what you're talking about in an equation. You need the dx there so everybody knows what you're talking about in an integral. Antiderivative is a word that we use when we're talking about integrals. And since we want to be able to use integral notation to find the area under a curve, we have to be able to find the antiderivative. Kind of like the not derivative. What you guys actually did on an extra credit sheet, just trying to reverse derivatives. And so this is the inverse of a derivative. It undoes it. Anytime we learn one function in math, we're always going to end up learning the inverse of it. So antiderivatives that go along with derivatives. So we're kind of undoing that. So finding the antiderivative of each of the following. If I told you that the derivative was x and I said, what was it like before? What did it look like before we did the derivative? Most people could probably, when you're kind of playing around with it, come up with a good idea. The formula to finding an antiderivative is to take it, whatever power it has, and when we did derivatives, we pulled it in front and -1. We're going to kind of do that backwards. We're going to increase the power by 1 and put it over that new power. So x squared over 2. And just to check to see if it would actually make that derivative, if I pulled the 2 in front, the 2 and the 2 would cancel, they would be gone, and that 2 would turn into a 1 because I'd subtract 1 off the exponent, so we'd end up right where we are. The thing with antiderivatives is you need to add a c on there, and that stands for constant because we don't know if originally this might have had a number on the end. And anytime we take the derivative of a number, we end up with 0. So we wouldn't be able to see if there was a number there originally, so we tack that on just saying, in case there was a number, we're covering our butts here by putting a plus c. Next one up says the derivative is x squared minus 3. So our original, whoops, without the tick mark, what it looked like before the original function, increased by 1 and put it over that denominator. And this right now has an x of 0, so we're going to increase that by 1 and put it over that denominator. So that is our antiderivative, and all we have to do is tack on a c. And that is our answer. The last one is just a 2. So it kind of works the same as that 3 did. I'm going to put an x to the 0 there. And so my function originally, what it did look like is 2x to the first over a 1. And then just add on your c. So moving on to actually evaluating some integrals, actually doing or working with the numbers that are on the top and the bottom. So when you go to evaluate an integral, you're going to focus on the function part, kind of keeping the dx off to the side as notation. We need to find the antiderivative first. So 2x will turn into 2x squared over 2 plus c. And then once you do the antiderivative, you move the integral to the end and you stretch it out and make it a straight stick. And -2 to 3. So you're telling everybody that that is the derivative. This is the antiderivative. And so now we're going to work on plugging in both of the numbers. So we're going to plug in a 3. So 3 squared is 9, just canceling those 2's. So I end up with 9 minus, what would happen if I plugged in a -2? And a -2 squared is 4. So the area under this curve is 5 units squared. So what you're doing essentially is finding the area from one place to another under this curve up till the x-axis. Number 2 is a 4x squared, so my antiderivative is going to be 4x cubed over 3 plus c, and we're going to evaluate that from 0 to 5. So I'm going to plug a 5 in. 5 cubed is 125. Hold on, I grab my calculator. And then we're going to times that by 4/3. So 125 and then 4/3. So I end up with 166.6 repeating. And then we're going to minus what would happen if I plugged in a 0. 0 cubed is 0, and then times 4/3 is 0. So our answer is just 166.6 repeating. Next one, I've got a squared thing here. We don't really have a reverse for the chain rule. As of such, we've only got so much time together, and we're not going to do all the integrals that are out there. So what we're going to do is FOIL this out first. So we're going from 0 to 4, and I'll write it twice right here. And we'll FOIL that out. So we'll end up with 4x squared plus 4x plus 1. Now I can do the antiderivative. 4x cubed over 3, 4x squared over 2, and then an x. Plus our c that comes along, and then 0 to 4. So plugging in a 4, I've got 4 cubed times the 4/3 plus, and you could do just a little bit of, if you wanted to reduce, you don't have to type all that in there. You just got a 2 times 4 squared, and then plus 4 on the end. So I end up with 121.3. And then again, minusing what would happen if I plugged in the 0. This would be 0, this guy would be 0, so would this one. So my answer is just 121.3. The last one has an absolute value of x. These guys are a little tricky. In order to do absolute value of x, we actually have to graph it. There's no antiderivative for absolute value. So we're going to graph it and look at that. If you've ever looked at a graph of absolute value, it's just a v right around the origin. And it looks like we're going to take this from -1, 1, 2, 3, 4, 5, all the way over there. And we're looking for the area under the curve, which is really just 2 triangles. So I'm just going to find the area of each triangle. So I need the base and the height of this triangle, and I need the base and the height of this one. So this one goes over 5, and if I plugged in a 5, I would also get 5. So the base and height are both 5. This one, the base is 1, and the height, if I plugged in a 1, is still 1. So doing that, plugging that into your calculator, again, there's no antiderivative, so all we're doing is just finding the area of both of these triangles and putting it together and getting 13 units squared. For our trig, since we were talking about trig when we did derivatives, the antiderivatives would then flip them back, so this is going to get a little confusing. For an integral, the antiderivative of cosine is sine, and then the antiderivative of sine is negative cosine. So those are going to be opposite of the way we learned them the first time, because now we're doing antiderivative. So this is the lesson on integrals, doing a lot of undoing our derivatives, so increasing the power and putting it over that denominator. This is the tricky part usually for students, is just getting everything plugged in the right way with all the fractions. So the more we do the antiderivative, the more fractions we end up with, and it gets tricky to plug all that in.